So the other day, I had a student come to me and ask me how he would go about modeling a wave spring in Autodesk Fusion. And I thought this was kind of an interesting question because a wave spring is kind of a complicated shape. It's not really easy to think about the best way to do this. If you are experienced with CAD, you might think this is relatively easy, but I'm certainly no expert. So um, I just wanted to show how I did this in Autodesk Fusion. One, because I didn't see any tutorials online that showed the way I did it. Um, and two, because I think it's a good example of why curve parameterization is useful in math and for this case. And it's a good kind of learning opportunity. So I just wanted to put together a little video about how I did this and talk a little bit about why it works. So, where do we even begin when we're trying to model this wave spring? It's a kind of complicated path. It's not immediately obvious how we would go about doing this. But the simple answer is that the way this is modeled is you've got kind of a continuous path. If you start at the bottom of the wave spring and you follow the path around and around, up and up and up, all the way to the top, it's continuous. It doesn't stop anywhere. It doesn't intersect the path at any point. It's just a continuous path. And because of that, we can take advantage of Autodesk's sweep function. If you come here to create under the solid menu, you go to create and sweep. We can sweep a sketch profile along a selected path. So basically, we start off, and if you look here, this was my original sketch. I created a 3D sketch of fit point spline points. And by creating this path in the shape of the wave spring, I was then able to sweep a sketch profile here, which is, you can see, 2 millimeters thick and 10 millimeters wide, along uh, the path of my fit point splines. That's what the sweep function does. So that's basically how it works. Now, obviously, you're asking, how do I even create those fit point splines? I mean, that's a really complicated pattern. I can't just throw those up there. And you're right. Calm down. I'm getting there. Basically, Inventor or Fusion rather has a utilities tab over here, and if you go to add-ins, scripts and add-ins, you'll see here there's an import spline CSV function, and if you click it, it'll prompt you for a .csv file. And basically, if you take a CSV file, like the one I've got here, this is actually a .xlsx file. If you take an Excel file and you put in points for x, y, and z as a function of some variable, here I've got it as t, you can come up with all the points for these fit point splines. So that's basically how it works. All right, let's talk about parameterization for a second. So all parameterization is when you take one variable and define it as a function of another variable. So in this example, x is parameterized, that is defined as a function f of t, or y is parameterized, that is defined as a function g of t. This is kind of the general form of parameterization. You might be more familiar with the parameterization y equals f of x. This is where we get x and y graphs when we're graphing in 2 dimensions. And this is an example of a parameterization. Y is a function f of x, where the function f of x is equal to x squared. This is how you get a parabola, right? So we've got y equals x squared. So if you wanted to get your y values for this graph, you would plug in a simple value of x. For example, if you plugged in 2, you would square it, and you would get that y is equal to 4. So if you come here at x equals 2, you see y equals 4. You can do this for all values of x and get all values of y. So that's all we're talking about when we're talking about a parameterization. So now, how does this help us with our wave spring? It is a complicated shape, but as it turns out, if you look at it from the top, that is looking at it in the XZ plane in Fusion, you'll see that it's just a circle. Circles are actually pretty easy to parameterize. So now you're thinking, okay, well, if I need to parameterize in 3 dimensions my curve for the spline points for a wave spring, well, I've got x and z taken care of if I can just parameterize a circle. So that's all we're going to do here. So in order to parameterize a circle, we're going to come back to the unit circle that you learned in trigonometry. So what we've got here is just an xy graph, and you've got a circle on it. And in order to think about different points on the circle, we can define it in two ways. We can define it in terms of our x and y points, right? For example, we've got here 1, 0 here on the x-axis to the right, 0, 1 on our y-axis at the top, negative 1, 0 at our negative x-axis on the left, and 0, negative 1 on our negative y-axis at the bottom. We can also think about if we have a constant radius coming from the origin, at different angles, we can get points along this circle. So we can think of those points as 0 degrees or 0 radians, 90 degrees or pi over 2 radians, 180 degrees or pi radians, 270 degrees or 3 pi over 2 radians, and then back here at 0 degrees or 360 degrees or 2 pi, whatever. So we go around the circle one time and we come back and suddenly we're at the same point that we started at. So it is a circle. It will keep repeating over and over again. So the sine and cosine functions are a good way to parameterize x and y in terms of the angle as we go around the circle. If we think about our angle theta, and we start here at our 0, we go up to pi over 2, then to pi, 3 pi over 2, and 0, our cosine and sine functions will give us values between 1 and negative 1. And this is exactly what we want if we're trying to parameterize our x and our y in terms of the angle. So if we use x is equal to cosine theta and y is equal to sine theta, we'll see that as we start here at 0, cosine, that's our x, is equal to 1, which is what we want, 1, 0. And sine, which is equal to 0, is what we want. Sine of 0 is equal to 0. As we come up here to pi over 2 radians, we get that cosine of theta, which is our x, is equal to 0. That's what we want. And sine of pi over 2 is equal to 1, which is what we want. And you'll see as you go around the circle, cosine of theta and sine of theta continue to model your x and your y. So we've just parameterized x and y in terms of theta. So now if we take this back to our wave spring, we can generally parameterize this as x of t is equal to the radius times sine of t, and z of t is equal to the radius times cosine of t. Here we're using x and z because in Fusion we were looking from the top down at our xz plane. So now we've parameterized x and z in order to get our circle. That is looking in the x and z plane. We've parameterized x and z. Now all we need to do is to get y, that is our how our function changes in y as we go around this path and we go up. How do we parameterize y so that it goes up and down in just the right way to get this complicated path that's useful for our wave spring? Well, I didn't come up with this myself. I did look at another YouTuber who did this in SolidWorks, and they used this equation. Y of t is equal to 7 times sine of 3.5t plus 3t. Now, when you look at this at first, this is a pretty complicated looking equation, but we can look at it in Desmos graphing calculator. And if we look at this, we see all this function is a sine function that's also adding some upward y translation. So as the sine function repeats, we are adding some amount to y as t increases. And that's all it is. 7 here out front is just the amplitude, which is essentially the distance from the bottom to the top here of the peaks. And then 3.5 is just affecting what our period is or our frequency. If I change this to say 7, you'd see it becomes twice as compressed. If I change it to let's say something like 1, not 71, 1, you can see it becomes much less compressed. So that's all that is. So this is the this is the exact form that he used for that. I found it useful when I was trying to create this to have the general form. And the general form that I came up with is 7r over 50, where r is your radius, times sine. I actually changed 3.5 to 3.8, and then plus alpha times t. I found that depending on what your radius and your thickness of your spring is, actually more dependent on your thickness of your spring, you should change alpha such that your wave spring looks nice. So it is kind of a guess and check game. I ended up making alpha 1.5 for the radius of 25 millimeters that I used. So yeah, that's all that is. So now if we come back to this Excel file that I created, these are the parameterizations that I've done. So you can see here for x of t, I've got 2.5 times sine of t, right? This is referencing my t here. And I've also got 2.5 times cosine of t for my z. And then I've got for my y, this more complicated equation, 0.35 times sine of 3.8 times 8.6, yada, yada, yada. I also have 3 sections because I did something different here with my wave spring. You can see at the top and the bottom of the wave spring, I've actually got it, let's see if I can show you. I've got it more flat here on the bottom and the top because I wanted to make it kind of nice so it could sit or be flat against any surfaces that were compressing it. So in order to do that, I altered the first few values of the spring and also the last few values, where essentially I just made the y constant for the first and the last few values. So that's all I did. And when you put all these into your Excel file, you do x, y, and z as the first 3 columns. That's all the input function in Fusion is going to care about. And you export this to a .csv file. If you go to Fusion and you then use utilities, add-ins, scripts and add-ins, and then use import spline CSV and copy that file, you should end up with the spline pattern. From there, you can use the profile, you can use another sketch, you can do the profile, and then you can sweep it along it to get your wave spring. That's it.